Hi everyone and welcome to your fourth lesson of low-level operations. What we're going to look at in this lesson is text storage and how computers store text. So hopefully by the end of this lesson you'll be able to describe what ASCII stands for. We'll be able to convert text into ASCII and vice versa. And finally describe how ASCII is used in computer systems. So we already know how computer systems store numbers, using binary. So all data used by a computer is represented by binary. So we know that that's a two-state system to represent power on or power off, compiled of all ones and zeros. Every number, letter, symbol, and control on your keyboard needs to be converted into binary so that the computer can understand it. So we're moving on from how computers store just numbers and how we can store text. So all of the keys on the keyboard are known as characters. That's also referred to as the character set. And they have a unique binary number allocated to them. So if you look at your keyboard, every single character that you can see there has a binary number that represents them. So the most commonly used code is called ASCII, and that stands for American Standard Code for Information Interchange. And that's what we're going to look at today, just how we utilize ASCII in computer systems and more how we store text using ASCII. ASCII uses 7 bits to represent each character, so therefore we can represent 128 different characters. We add a leading 0 to the 7 bits, therefore each character requires 8 bits or 1 byte of storage. ASCII is a standard file format, which means it is recognized by all computer systems, and therefore text can be transferred from computer to computer and it will be recognized. So this is a really good advantage, and that's why a lot of software packages and stuff use ASCII, because they can just transfer information across many different platforms and it will be recognized. So ASCII is a universal standard that is recognized worldwide. Now if you think of your keyboard and all of the keys that you see, can you see why that would be a problem if all across the world we only used ASCII? I'm going to show you what the problem is. What about French and German and all of their special characters? Think of the French alphabet and all of the accents that you have above certain letters. What about languages that have different shaped letters? For example, Chinese. There's also Arabic, Egyptian, Japanese, Russian, Urdu, Turkish, Greek, Korean. If you Google those alphabets for each language there, you'll see there's a plethora of different characters and symbols all within their character sets. So in order to solve this problem, we use the standard character code called Unicode. Now Unicode uses 16 bits, which is equivalent to 2 bytes, to store each character, therefore giving us 65,536 different characters. So that's way more than enough to store every character for every language in the world, which is a real advantage. Now the only disadvantage of using Unicode is that it will take twice as much storage than ASCII. So it will use up more memory in your computer system to store. Each character will need 2 bytes of storage rather than the 1 byte that we currently use for ASCII. So when talking about characters, it's important that you're able to differentiate between the two types of characters that we're going to look at. So on the left hand side of the table is what is known as printable characters. So that's all your lower and uppercase letters, your numbers, and all of your symbols. They're called printable because when you click on them on the keyboard, they appear on screen, so they print something onto the screen. On the right hand side of the table then is what is known as non-printable or control characters, and these are things like Shift, Alt, Delete, Tab, Backspace, and Return. The reason they're called control characters is simply because you control the text when you click those. So if we use, let's take Return for example, you can move and manipulate the text, but it doesn't actually print anything onto the screen, therefore it's referred to as a non-printable or control character. Now what I said last time is that it's important to remember that each character on the keyboard has a unique machine code representation, and machine code is just another word for binary. So every single character there in that table has its own unique binary number that's represented in the computer system. Now those unique numbers is then what we're going to look at just now. So translating plain text to ASCII, okay, and remember ASCII stands for American Standard Code for Information Interchange. So if we have one word that we want to type onto the keyboard, how is that then going to be represented in a computer system? So if we take hello, for example, notice the H is capital, and that's very important to remember, okay? I'll explain why just further, but if we take hello, for example, the way the computer stores this is it breaks it down into the 5 characters, okay? So here's 5 printable characters that you can see. If we then take the capital H, we use this diagram on the right, which is known as an ASCII table. And now this has 128 characters here. So capital H, we go to and locate it on the table here. And that number, or the code, the ASCII code that represents capital H is 72. So if I wanted to translate capital H into ASCII, I just locate it on the table and put the number here. So it's 72. We then move to small e, locate that on the table, which is 101, and we pop it there. Okay, and I've done that for the whole word hello. Now each of these numbers is the code. Okay, so 0 to 127 is the 128 different characters that we can store, but we know that in the computer system each of these numbers would actually be translated into binary and then stored. So I mean, you could do that yourself, no problem. We all know how to translate 72, for example, into binary, but for this task you won't need to do that. Okay, we simply just have to identify each character of the plain text, identify the characters, and then locate their unique code from the table. So then vice versa, right, if we want to convert from ASCII into plain text, so here you have just a random list of numbers. These represent the ASCII codes, okay, for certain characters on the table. So if we take 78, for example, I would then just look for code 78 and notice that that is a capital N. Now remember I said it's really important to remember about capitals and uppercase and lowercase letters. I choose my name as a good example because there's an N at the beginning and an N at the end. So you would maybe just assume that the ASCII values are going to be the same, but that's not the case because it's an uppercase and a lowercase letter. So capital N is 78, whereas a lowercase n is 110. So if you were given this ASCII code here without having the plain text underneath, you would simply just locate the number on the table. So 97, try and find 97, which is a small a, and pop it in the box. Okay, so that's how we just translate ASCII to plain text and vice versa. So your task for this week is to complete the attached task sheet, which is called 4B Text ASCII Code. It has all of the questions that you'll need to answer there, but it also has this table on page 2 for you to answer the questions, so you don't have to refer back to this video. It's all going to be in the one document. You should then submit that via Show My Homework by next Friday, the 5th of June. If you're unable to access Show My Homework or you're having difficulties uploading it, just add a comment and I can send you my email address, no problem. If you have any questions about this work or any of the work to date, just reach out to me as soon as possible and I'll try and get back to you, okay? But good luck with this task. It should be a lot more straightforward than last week's lesson. But again, any questions, don't hesitate in reaching out. Okay, good luck.